Today, we are diving into one of the greatest marvels of human biology, one of the biggest mysteries out there, how our brain creates and understands language. I mean, really think about that for a second. How does this squishy 3-pound organ sitting inside our skulls manage something as impossibly complex as language? Everything from a simple, "Hey, how's it going?" to the most beautiful poetry you've ever read. It's all happening right in there. So the field that's dedicated to cracking this code, it's called neurolinguistics, and it's this amazing mix of neuroscience, linguistics, and psychology. Today, we're going to go on a little journey through this field. We'll start by seeing how we drew the very first map of language in the brain, and then we'll see how modern science has basically had to rip that map up and start all over again.
Now, our story doesn't start with fancy, high-tech brain scanners. Nope, it starts way back in the 19th century with doctors and scientists who were just carefully watching patients who had tragically lost their ability to speak. This condition, aphasia, it became this incredible, crucial window into how the brain works. By studying what a person lost, scientists could start to figure out what those specific parts of the brain were responsible for in the first place. It was kind of like reverse engineering the mind, all based on careful observation. So let's meet a couple of the key detectives. In 1861, you have Paul Broca. He had a patient who could only say one word, tan. And when the patient passed away, Broca found damage in a very specific spot in the left frontal lobe. We now call that Broca's area, and he linked it to producing speech. Then, a little over a decade later, another scientist, Carl Wernicke, he identifies a different spot, this one in the back of the brain that was crucial for understanding language. That became Wernicke's area. For the first time, we actually had a model. The idea was that language lived in these specific centers with pathways connecting them.
And this quote right here, it just perfectly sums up the monumental takeaway from that whole era. Damage here causes one type of problem. Damage there causes a totally different one. Location mattered. Simple as that. A simple, pretty elegant map of language was born. But, like all early maps, it was missing a lot of detail.
Right. So as scientists studied more and more cases, it became pretty clear that the real world was, well, it was a lot messier than their neat little diagrams. This classical model was about to run into some serious trouble.
This is just a perfect analogy. You can learn a lot from a car wreck, for sure. You can see which parts are broken, which parts are crumpled up, but what you can't see is how all those parts are supposed to work together when the engine is actually running. Studying brain injuries had that exact same problem.
Yeah, the problems just started piling up. First off, damage from a stroke or an injury, it's almost never a neat little hole. It's usually widespread. It affects all these deeper parts of the brain, and it's totally different from one person to the next. Then came the real kicker. Researchers started finding patients who had all the symptoms of Broca's aphasia, but no damage to Broca's area. And they found other patients with damage right in Broca's area who had completely different symptoms. The simple one-to-one map, it was clearly breaking down.
Now this is where it gets really, really fascinating. Check this out. On the left, you have patient JR. This person could handle verbs just fine, like adding ed to make something past tense, but they absolutely could not do the same thing for nouns. And then look at patient RC on the right. This person had the exact opposite problem. They were fine with nouns, but couldn't handle the verbs.
This kind of thing, it's called a double dissociation, and it was a total bombshell. It's basically scientific proof that two related things, in this case processing nouns and processing verbs, can be broken independently. So what did that mean? It meant the brain wasn't just handling language as one big thing. No way. It was breaking grammar down into these incredibly specific, separate jobs. Our simple map? Yeah, it needed a serious update. Okay, so this is where everything changes. The next chapter in our story is all about technology. Because for the very first time, scientists were about to get a peek at the brain not after it was damaged, but while it was alive, thinking, and talking.
And remember that car wreck analogy?
Well, if the old way was studying wrecks, this new era was like finally getting to pop the hood of a running engine. At last, we could see all the parts moving, see how they connected, and really begin to understand the system as a whole.
Suddenly, scientists had this amazing new toolbox. You've got things like MRI giving us these crystal clear pictures of the brain's structure. Then there's fMRI, which shows us where the action is happening by watching the blood flow. And other tools like MEG can tell us exactly when things are happening right down to the millisecond. So for the first time, we could see the structure, the location of activity, the timing, and even the brain's wiring all at once. It was a complete and total game changer.
So with all these powerful new tools, a completely different picture of language started to emerge. It wasn't just a handful of centers anymore. Oh no, it was something way more dynamic, way more interconnected.
And this might be the best way to think about this shift. The old view was like a library. You had your grammar section over here and your vocabulary section over there, all neat and tidy. The new view, it's much more like the internet. Language isn't stored in one place. It's a process that calls on these huge distributed networks that stretch all across the brain, with information zipping back and forth between them.
So when you process the grammar of a sentence or figure out what a word means, it's not one little light bulb going off in your syntax center. Instead, it's a whole constellation of different areas, a massive network, all firing and working together.
This modern view has really given us three huge revelations. 1, the brain isn't neatly carved up into special language-only parts. 2, the brain systems we use for language are actually interconnected with all sorts of other thinking systems. And 3, the whole thing is interactive. The sounds of words can influence grammar, grammar can influence meaning, all at the same time. And this really matters, you know? It helps us understand things like how the brain can rewire itself after a stroke, or how learning a new language can literally change your brain.
But here's the thing about science. This new, more complicated map hasn't solved everything. Not by a long shot. In fact, it's opened up a whole new universe of profound, really exciting mysteries that scientists are working on right now.
For instance, we've known for more than 100 years that language is mostly a left brain thing. But modern brain scans almost always show the right side of the brain lighting up during language tasks too. So, what is it actually doing over there? We still don't really know.
Here's another huge one, plasticity. When that language network gets damaged by a stroke, how does it recover? How do other parts of the brain manage to step up and take over some of those lost jobs? If we can figure that out, it could lead to much better therapies.
And what about those brain areas, like good old Broca's area, that seem to be involved in, well, everything? It pops up in studies on producing speech, understanding grammar, and even things like general decision-making. How can one little piece of brain tissue be such a multi-talented superstar?
And finally, just think about this. You can understand what I'm saying right now, even if you're in a noisy coffee shop or if I had a really thick accent. Our brains just handle that. They create stability out of all that variability. How on earth does our neural system pull off that incredible magic trick?
From a few simple dots on a map to this vast, dynamic, living network, our understanding of language in the brain has been totally transformed. But the quest, as you can see, is far from over. Because in the end, the story of how our brains make language, well, that's really the story of what makes us human.